Okay, so first, congratulations on 30-year of age. We've been friends for a long time, and it's just wonderful. 30 years. I had the privilege of working with VJ and a lot of guys at VJ. I have benefited so much from the relationship. I don't know why you keep asking me back. I'm the one that gets all the good stuff, you know. But thank you very much. And I've been honored. It's been my privilege to work with you guys. And thank you to all the great talks before. Gosh, they're very, very good. The visions you've been casting are really interesting. It got my head spinning. I remember at Livermore, we used to talk a lot about data fusion, you know, fusing sensors from ultrasonics and thermal and all that stuff for some aerospace parts. We were part of the return to flight for the shuttle, and we had all those. And it really was interesting what you said, that Hanky, that if I pronounced your name right.
Yes, right.
Oh, okay, good. When we started passing different types of NDT information around, it changed our scanning techniques. Because we weren't interested in an edge. I wanted to know the material. You know what I mean? It's kind of interesting. So there's almost a couple perspectives, but that's probably another talk. Okay. So one of the ways, we thought I'd talk about, and this is just a discussion. I'm an informal guy. You've got a question, just put your hand up when it comes out. You know, it'd be fine with me. Some properties of a fully autonomous CT scanner, you know, walking around the street, ordering things. The self-adjusting scanners, how they might work. And you've already talked about some of that already. Some of the scanners. But I'd like to talk a little bit about how that varies with different applications. I'd like to talk about some of the requirements for a fully automated scanner. And then one of the things, I really appreciated the talk from Kuka, Dirks, and you know, with the cloud and everything, that's really good. One of the things that I know VJ and I run into when we're doing inspections for people is, you let that data out of my sight, I'll kill you. Right? Data out of this building, not gonna happen. I mean, take baggage scanning that we'll talk about. You can't let somebody else have that data, you know? And so our approach is maybe a little different. We're trying to take physics models and physics centers and embed it in the scanner. You know, as the variant guy said, you know, PCs are pretty powerful. We can put a lot of physics in there. You know, X-ray baggage scanners have done that. They have put physics, sensors, all that stuff in there, and they operate by themselves. So we like that idea. Although I love the cloud. I mean, there's nothing wrong with it. It just, what are you going to do when they pull the internet cable out? You know, it's stuck. Okay. All right. So, and then this, I'll make a comment on designing test objects if you still have patience and haven't met for the door. Okay. So, DR and CT scanners perform many critical tasks. I don't need to bore you with this. You saw a lot of examples on porosity and voids and finding high attenuating materials in the wrong place, gaps or component lengths. You monitor manufacturing process for consistent operation. And I really appreciated that one application you showed, only 45 views. We did a fuel rail for Ford. 90 views was fine. It was all they wanted to see. You could do a bunch. And so when you really think about it, you want to monitor a manufacturing process for consistent operation, there's this measuring as-built boundaries and dimensions, and you know, you can do that in VG Studio, take your volume, put it in VG Studio, and generate drawings in a number of formats. You know, Ford's been doing that for years at their facility. At the product development center, they make the part, test the part. They don't draw the part. They scan the part. The scan generates the drawing. And when you think about it from a new product point of view, it's a better idea. And how many times have you ever compared an as-built to an as-drawn part? As-built wins. I mean, it just went clear. You're nodding your head. It really wins. It's as-built. You want to go with as-built because as-drawn and as-built, they kind of diverge sometimes. Then converting CT scans to mesh input, that's kind of been done, and we all do that. I'd like to talk about this kind of being a materials characterization for unknown or contraband materials in various loads and transports. You know, you're talking about garbage, scanning garbage. What's in garbage? Lots of stuff. Anything you didn't want ended up there, right? So that's kind of interesting. Okay, and that's kind of what I'll be focusing on in this scanner, recognizing all the wonderful work that's been presented up here already, and that VJ people do, Fraunhofer does, in scanning. And so you can look out on, and I'll mention this a little bit more, you can look out on all the NDT applications and sort them into 4 boxes. Single material, single object, simple object, single material, complex geometry, multiple material, simple, like layered cylinders, and then multiple material, complicated geometries, bags of people's luggage, bags of garbage, things thrown into trucks. Anyway, okay. So that's going to kind of hover over these comments that I'll make here on this autonomous scanner. Okay, I'm not even going to talk about this. You guys know this is a scan of a, and you can get 3D dimensional measurements. And this is a simple object, really, by a lot of standards. It's an aluminum engine block. It's got steel inserts in it. You can pull everything out, all the dimensions, all this stuff, and do it to 200-300 microns. So you guys know all that. Now, baggage scanners are a little different, right? You don't know what's in there. Is that wine in there? Is it oil? Is it something you don't want? I've looked at a lot of bags. I was the senior scientist for 3 years for the certification effort to certify every scanner that's in the field right now. And so I worked for 3 years at Tyndall Air Force Base from the lab, going through the certification process. And I remember I had to look at 7,000 bags from LAX to Newark. I still have nightmares about one bag I looked at. It was a mannequin maker. He had 9 mannequin heads in his luggage. And I still wake up at night thinking, oh God, 9 mannequin heads. But I mean, this is a tough object right here, huh? It's really, oh sorry, I'll get this right. This is really a tough object. So, and it's got to be done fast, right? You've got to do your acquisition, reconstruction, segmentation, classification right in through here. And then it's all got to be tagged and sent back. It gets to the airplane or it doesn't. So you guys have all put your bags through things. You've seen the little piece of paper that's in your luggage. That means they opened it up. It's actually been kind of a nice thing since they've installed, check bag. There's less theft because it's all on video. Interesting. Okay, so what currently fielded security scanners do now? So they've been, for the last 10 years, we kind of had part of requiring this, they acquire data at 2 energies. They process and reconstruct data from those 2 energies to enable the classification of all the materials in the bag. They can detect and identify contraband materials at different volumes. Now, when they do their dual energy stuff, the problem may be a little tougher. You're not looking for differences of 3 Z units. I want to know the difference between RDX and Emulex. I want to know a Z difference of 1/2. So what kind of signal to noise do you need in order to get a Z difference from 2 CT scans, one that has good penetration, the high energy channel, and one that has lousy penetration, the low energy channel, in order to do that in minutes? It's a tough job. But in order to do this, Ying and Carl Crawford and Ying, I'm sorry, I forgot his first name. Anyway, they document this in a paper. They constantly monitor the source output and spectral content. So every view, they monitor what the effective energy is that hit the detector. Now, remember, it's not the effective energy that's in space. That was from your source. It's the effective energy you stopped. That's the only one in the room that you're interested in, right? It's only the energy that you stopped that does any work for you. And they monitor that, and they actually change the projection data if that, I'll get this right, sorry. They change the projection data if that changes. So there's a constant feedback loop, constant data-driven feedback loop right in the scanner that allows you. And then they have built-in verified expected values for bags and their contents. From these 2 reconstructions, they generate a pure photoelectric and a pure Compton reconstruction. And they have embedded in there the X-ray tables. I'm really, I know, drinks are soon. But embedded cognition of mechanics to drive this Compton photoelectric decomposition. So that's how you do it, right? You have to monitor the source output. You have to build in expected values of bags. You have to build in some physics. Okay, so fully autonomous DRCT scanners, and this is for the multi-material case, okay? I'm not really applying this. You know, I think it's interesting. We're all pushing value CT. And when you think about it, value CT may be the toughest CT job. Somebody that knows very little about CT, hey, let's scan this. And they put it in, right? And it's tough. It's, you know, when we're doing something in a plant or something like that, we have a model of the part. We have the manufacturing of the part. We have somebody present the process on how the part was made. Anyway. So it's fully self-calibrating, can sense when the detector is drifted and recalibrate the detector. You know, this shouldn't be periodic, right? I know everybody, what does everybody do now? You calibrate the detector on some period. Is that the right way to do it? Probably not. Not if you want the best signal noise. You can sense when the detector has too many bad pixels, and you shut down. I remember we had to go to one airport. I won't mention what it is. They had a scanner that was always passing bags. So they put the bags through that one. We had to, wait a minute, the detector's toast. No wonder it passes the bags. You know, we got all the statistics from all the airports, and we went, oh boy, that's 99% bags that are passing. Anyway, so you know, you don't, you know, and then they fixed it, you know, and I mean, these things happen. You want to be able to save and archive all the motion information with each view. As you saw in that 45 degree, as you said in that 45 view application you have, you know exactly what view you're at. You know where the source and detector are. If you know that, you can make a lot of a very few views. If you don't, you're kind of toast. So you have that. You have an automated scan of a test object or an alignment object that you go get and do whenever you need to, not when, okay? You monitor the source for each acquisition. Then, you have to have enough physics in the scanner to recommend a scan energy and a beam filtration. Now this doesn't, I think Cliff, you did a paper on that. You did a paper on how to pick the energy and beam filtration for objects. Nice piece of software. That's available, and it doesn't, you know, you can run it. Scanner recommends a set of, the one I like is recommending a set of basis materials and or a set of collimation strategies. The scanner recommends a rescan. That's a better idea, right? If you take bad data, you should throw it away. You should just throw it away, right? The scanner configuration might be quite different, though, between, you know, we have exploratory scanning and focus scanning. And then the last thing is, with X-rays, you can only scan what you can penetrate. And you know, taking Inconel and putting it in front, an inch of Inconel and putting it in front of a 130 kilovolt machine is just not a great idea. Okay. All right. So sources of variation. So what you have to do for these automated scanners, right? We have to get after these sources of variation. We talked about them: detectors, motion artifacts and alignment, X-ray source variation. These are the ones that are the toughest, right? I'm sorry. I'll get this. Maybe I won't. Okay. These are the ones that are the toughest. Object-based artifacts from single or multiple angles. You know, I mean, sometimes in baggage scanners, you have changing X-ray attenuation mechanisms. So how does X-rays go? Rayleigh, photoelectric, Compton, pair production, right? And when you cross those boundaries, where the actual mechanism of the physics changes, the significance of your voxel changes. And when you cross those boundaries in a violent way, like you do in some baggage scannings, you get weird streaks. There's a large difference in X-ray scatters, you know, in that kind of circumstance, and then, you know, localized high attenuating components are just tough. Okay. So, you know what these remedies are, and some of them are already done. You calibrate on a regular basis. You capture the object motion at each measurement, and You do periodic scanning of geometric test objects. You do X-ray source variation, you measure this. Now this is where some kind of physics measurement, it would really be nice if we could develop physics sensors that would measure the full spectral content of the X-rays, right? Then if you want to drive a statistical reconstruction or an iterative reconstruction, you're driving it with the real thing. And then there's remedies for object-based artifacts and just changing the scan energy and changing the collimation. Iterative codes and statistical reconstructions, they go a long way. I think, again, you have to look at, like for baggage scanning, it's been kind of tough for baggage scanning. You don't know what's in the bag. You don't know where to start. You don't know if you've really fully penetrated. With other objects, things you know about, that you made this part, you know pretty much what's in it. I think iterative codes have a lot of advantages. Okay, so these are the functions that we have to build going forward. I don't know why I'm doing that. Embedded detector calibrations. Let's say to variant, we need some way to detect, have a processor in there to recalibrate the detector whenever it starts to get problematic, right? Taking data with a bad detector is wrong. We need position information captured all the time. And an interval set up for scanning geometric test objects. X-ray source variation. I like pure material references. Pure material references. And what I mean by that is, the only real way to know what energy you had, take two pure materials, radiograph them, and then you know what energy you're at. Up till that time, you kind of don't know, right? Okay, and the scanner is capable of an auto rescan. I think that's a good idea. Okay, and the full reconstruction of a volume can use information from a scan where you didn't penetrate and a scan where you did, right? You can use the edges, the outside edges from something where you didn't penetrate and reconstruct as well with the stuff that did. So, anyway, it requires good workstations, but you knew that. Okay, anyway, I just thought a couple things for directing a rescan. We need embedded and verified modeling of source spectra. Have any of you looked at, there's a lot of codes for source spectra. I counted 6 out there. There's a very well-known paper that actually measured it. Only 2 of them came up to be accurate. That's kind of interesting. Verified model of source intensity divergence, verified models of detective stopping power. And when I say verified models of detector stopping power, I mean like at high energy, after buildup. You take detector stopping power, I've stopped cesium iodide. Well, you stopped in the cesium iodide, but the next view is within the fall-off tail of the one before it. And by the way, if you leave your LINAC on for a long period of time, that tail gets longer and longer. Now, we all know that, but how many correct for it? And some measurements for a range of different materials that should be in the object. And I like this. We like to, I know we're experimenting with this, embedding our physics tables and physics measurements into the scanner. Why not? It's not that much. Okay, so I just thought I'd talk about one application and then I'll be done. So this was our idea. One of the other things baggage scanners do, and we built in here, is this. You don't have to take, for unknown materials, you don't have to take the full set of data each time, right? If you know what's in the bag and it's okay, it's not past threat mass, you can pass it. Scan time is something that's just as variable as anything else. Why spend all your time on something when you figured out what's in the object? You only need the minimum, but you may need the maximum at a certain time. So our goals for scanning were to identify the contents of waste drums, characterize and find a signature for different types of absorbents, and then only scan the amount that is required. If a couple of DRs are fine, like a couple DRs, and you know what they are. If area detector CT works, it's quick, you're done. But from the area detector CT, if you find that you've got scatter streaks you can't unravel, do an LDA. So this fully automated scanner for these difficult situations may have access to more than one detector. And it's kind of nice. You can see the difference. So we take our basis materials, we put them around the drum, we scan the drum, you get a radiograph with the basis materials, we scanned it with a amorphosilicon panel, and then we had some areas in here that we really wanted to know what they were, so we went with the LDA scan. And notice these two are very close, but this is the measurement you can calibrate. I'm seeing if you guys are awake. Now I got fat thumbs. There we go. All right. Anyway, sorry. This is the measurement you can really calibrate. Time after time, you know what the average energy is. It's collimated down to a slit. You've got your physics right in order to do that measurement right. Okay. So how many of these do you know, not every drum is going to go through all this process. If you get done with this and you know what it is, you're done. If you're satisfied with this, you're done. If this one, well, then you have to spend a lot of time. Okay, I just wanted to say, you know, putting all the physics tables in isn't that important, right? This is a plot of the Hounsfield units at high energy, right? And look at how flat some of these things are. A copper, you got pair production starting at about 3.5 MeV, but this is pretty nice, isn't it? If you said find materials in this range, well, gosh, I can from 1.5 MeV to 4, you know, these materials don't cross each other. That's kind of nice. High energy scanners are kind of nice that way. Okay, so I think I beat that to death about the different types of scanning. I mentioned it early. And another challenge comes when as soon as you can do CT, somebody gives you a part that's way bigger than your detector, and then you got to do something different. And you got to do either a ROY scan or a half scan, offset scan, or any one of these scanners. And the only way to fix that is probably more modeling. And I really think that you have to, in our work, modeling the reference irradiance is really critical for us, knowing what that is. We can progressively model the missing data, but we have to have these at hand in order to do any of that work. What I was going to say about data fusion is that what numbers do you want to pass from X-ray to someplace else? It's quantitative CT, I think. I think that's where we want to go. Once you have density, once if I could really measure the density of the material, I pass that number to you and I say, that's the density of that material. Well, that changes all the talk in the room. It wasn't attenuation, it wasn't anything, it's density. Measure it with a water volumetric thing, it'll be what I tell you it is. So this is kind of, it usually is when you design CT scanners, you have system speed, spatial resolution, and contrast resolution, right? And if you want to go fast, you lose contrast, or you lose spatial resolution. You know, you're always operating in this envelope. Anybody who's designed scanners goes, yeah, we got to pick somewhere in here. I think the other axis for quantitative CT is knowing what energy you're scanning with. And I don't think you can ignore that. And I just, you know, for building material objects, medical is a great example. Notice that they put different materials in the mix, and we should too, in all our test objects. Okay, so for autonomous scanning, I think this is very doable right now. Focus scanning applications can be automated to a large extent. I think this is hard. This is sorry, late in the day. I think exploratory scanning is hard. I would recommend, we have found a lot of value in multi-material test objects, and I can't say enough about putting embedded X-ray attenuation physics and physics sensors into your scanner. Okay? All right. Thank you.